Welcome. This is the lecture for Chapter 14 on consumer surplus. A good bit of what you will see in this chapter really is just review of what you already saw in Principles, consumer surplus. The key difference and the extension is showing you mathematically two different ways to quantify in dollar terms the amount of utility gained or lost by a price change. This is important because frequently government policies implement functionally price changes. And if you want to do a cost benefit analysis, you need some way to express the benefit to people or the cost to people in their gained or lost utility. You need to be able to express that in dollars. So here's an example. You can buy as much gasoline as you want at $1 a gallon once you enter the market. What's the most you would pay to enter the market? Well, if you enter the market, you will conduct transactions and you will get some gains from trade. Your utility will go up. You'd be willing to pay the dollar value of that utility, the amount of money that to you would be equal in utility to those trades. Okay. Here are the three ways we can look at it. Consumer surplus, equivalent variation, and compensating variation. Equivalent variation and compensating variation are the two ways I mentioned of calculating a change in utility in dollars. Why they're called variation, I don't know. I was thinking about that, and I do not know why they called it that. Now, bit of review. Reservation price. That's the most you're willing to pay for something. If this is you, then you'd be willing to pay, hypothetically, $10 for the first gallon of gas. For a second gallon, you'd be willing to pay $8, etc. Now, if you can enter the market at this price, say $5, and you do enter the market, then your surplus, your consumer surplus, would be this green area. This first gallon, it's worth $10 to you. You only had to pay $5, so you gain $5. Plus, the second gallon, you would have paid up to $8. You only had to pay $5. You think it's worth $8. You paid $5. You gain $3. That makes, what is that, $8 altogether? You just total up the green area. And that's the total consumer surplus from conducting these transactions. This just shows the same thing, but in half-gallon units. You just see the columns get a little narrower. And if you could buy it in any amount, then it would no longer be the stair step. It would just be the area of that triangle. You should have seen all this before in Principles. Okay. Now, let's look at how utility changes, how consumer surplus changes when there's a price change. Okay, here is the inverse demand curve. Price on the vertical axis, quantity on the horizontal. At this price, you will purchase that quantity. This would be your consumer surplus, the blue area. Now, price goes up. to P1 double prime, this would be your consumer surplus, and the difference is that black area. That would be the loss in consumer surplus. Looking at it as just change in consumer surplus, you can calculate the area of that trapezoid. Now, there are two other ways to look at change in utility: compensating variation and equivalent variation. Let's go to compensating variation first. Price of something goes up. You're going to be worse off, assuming you purchased any of it. How much money would I have to give you so that you'd be equally good off as you were before the price change, to compensate you for the price change? This should be reminiscent of the Slutsky decomposition. Actually, it's more analogous to the Hicks decomposition, which this book doesn't address in any depth. You remember in Slutsky, you looked at moving the new budget line to the old consumption bundle. Well, in the Hicks decomposition, you'd move the new budget line to the old indifference curve. That's a little closer to what we're doing here. All right. You start out, whoop, if I can, there we go. Certain price of thing 2, certain price of thing 1, which gives us this budget line. You have preferences. Here's an indifference curve, so you optimize there. Now, assume the price of thing 1 goes up. If it does, well, this end of the budget line is going to stay where it is. But this end will swing in, so that now you're on this green budget line. You will reoptimize. This is a lower indifference curve, meaning a lower level of utility for all of these. Then you'll reoptimize to there. So, assuming that your income doesn't change, you will still be spending all of your money, but you won't be as good off. Now, this graph is a bit messy. You started here. You reoptimize to there. You're worse off. You're on a lower indifference curve. You're on U2 instead of U1. These are indifference curves, but they're labeled as U because all the points on each have the same utility. Okay. So the price of thing 1 went up, and you're worse off. Your budget set is smaller. Instead of that being your budget set, now this smaller area is your budget set. You have fewer choices. Okay. How much money would I have to give you to compensate you for this price increase so that you would be as good off as you were before? Well, here's one way to define as good off. We could say, how much money would I have to give you such that at the, if I can find my cursor, it is here somewhere. There we go. At the new prices represented by the slope of this new budget line. Given that you have to live with the new prices, they won't change, but how much income would I have to add so that you would reach your old indifference curve? If you're on the same indifference curve that you were before, well, from that perspective, you are equally happy, equally good off. You haven't been harmed. Well, remember that for the budget line, the slope represents the price ratio. But how far in or out it is from the origin represents income. So, essentially, what we're asking is, at these new prices, so at this new slope of the budget line, how far out would I have to push it? How much additional money would I have to give you so that you could end up here, just barely able to afford a consumption bundle on the old, higher indifference curve? Well, this difference here is just a dollar amount. Think of it this way. If you spent all your money on thing one before and after the change, well, instead of being here, you would be here. This is a quantity of thing one. Divide it by this new price, and you have a dollar change. Okay, that's compensating variation. How much money would I have to give you after a price change so that living with the new prices, you would be as good as you were before? There's another way to think of it, called equivalent variation. Equivalent variation is asking how much money, essentially, would you be willing to pay to avoid the price change? The difference between the two is which set of prices are you going to have to live with? If I say you're going to have to live with the new prices, we've already changed the prices. How much money do you need to be made whole so that you're not hurt? Living at the new prices, with the new prices. That's compensating variation. Equivalent variation is saying, how much money would you be willing to give up to stay at the current prices, to avoid the price change? To stay at that budget line slope. Well, here you are again moving the budget line, but instead of maintaining the new slope after the price change, you're keeping the old slope before the price change. In both cases, you're doing the same thing. You're just measuring it differently. You want to know, what is, in dollars, the distance between U1 and U2? Here, the distance between U1 and U2, for the blue point and the green point, in dollars is that amount divided by the price of X1 at the new price. It's this distance measured at the new prices, because both lines have the new price slope. Here, you're doing the same thing. You're measuring the distance between U1 and U2, but at the old slope in both cases. This is an example shown in your textbook on page oh goodness, I've forgotten. I think 249, somewhere around there. It is labeled as figure 14.4. It shows side by side a price increase. I know this is a little busy, so let's try to step through it one bit at a time. You start out in both cases, and it's not writing. Here we go. You start out on the same budget line in both cases. And in both cases, you experience a price increase. It's X1 on the horizontal axis that gets more expensive. So the point where the budget line intersects the vertical axis doesn't move. That's a pivot point. X1 is more expensive, so it just swings in to there. And you reoptimize. In both cases, you start there and there, and you reoptimize, if I can see it, to here and here. The question is, and the difference between the two is, how far apart are these two indifference curves? On the left-hand case, you assume the person is going to have to live with the new price ratio. So you keep the slope of the budget line, of this new budget line. You just add income, so you shift the budget line right at the same new slope until it is tangent to the old higher indifference curve. Here on the right, the equivalent variation is you avoid the new prices. You tell the person, by paying a certain amount, you can keep the old prices. You can keep this slope. Well, how much would they have to pay? If you move the budget line to here, they would be exact. If you gave up this amount of money between this budget line and this budget line, the person would be on the same indifference curve as if they hadn't paid to avoid the price increase, which means this person views the dollar value of this difference as the dollar value represented there. Okay, that's the difference between compensating and equivalent variation. If you're comfortable with the Slutsky decomposition, at least graphically, this should seem pretty straightforward. It gets a little trickier when you're doing the math. I'll show that to you in the homework walkthrough next. Thanks for watching.